Hello everyone. Today we are going to be looking at two-dimensional figures, and essentially we are looking at polygons. We're going to start with how we can classify each polygon, and then we're going to move on to how to find the perimeter of various types of polygons and a little bit of information about circles. So let's begin with what a polygon is. There are a lot of different definitions of polygons, but the one that we're going to work with is this. It's a fully enclosed region that consists only of segments. And in this, that means that each segment is going to be called a side of the polygon, and each endpoint of a side is a vertex. Now, all the figures that you see here are polygons. You can tell they're polygons because, well, they're fully enclosed. There's not something where you have an open end somewhere like this. That would not be fully enclosed. And a region is just saying it includes both the inside of the figure and its boundaries, so these lines, these sides around it. Also, the fact that it consists only of segments is just saying that a polygon will not be something like this. That's not a polygon because those aren't segments, that's a curve. The only exemption to this is a circle, which technically is just a series of vertices rather than a curved line. Now with this, each side is going to be a segment, so that means if I have my figure here where we have a triangle and I were to label this A, B, and C, I could refer to the sides of this triangle as AB, AC, and BC. And I would label them that way so that the side would be AB, BC, and our remaining one AC. Vertices are just these points, A, B, and C. And you can list them that way, A, comma, B, comma, C. Those are all our pieces of information as to what a polygon is. However, we have a lot of different ways that we classify them, and we're going to deal with 3 different classifications that we use. Now, the first one's pretty self-explanatory. What we're looking at is the number of sides, and they have special names for them all the way through to about 12, and that's when we stop giving them special names just because we don't see them as often. So with these, please notice that the prefix is the part at the beginning of the word. It's going to really tell you how many sides you have, and you might recognize these from science. You've got triangle, tri being 3 sides, quadrilateral, quad being 4, pentagon, 5 sides, like the pentagon. You've got hexagon, 6, heptagon, 7, octagon, 8, nonagon, 9, decagon, 10, and dodecagon is 12. Now we're skipping 11. 11 has several names, and frankly, we don't see it all that often, so we're just going to skip it. Now once you get past that, we're just going to call them n-gon, where n is just the number of sides to that. So you could call it a 15-gon or a 20-gon. Any of those will work, and they won't use the specific name. Now you might notice that these look very different, and your idea of a pentagon might look incredibly different from the one that they drew. That's fine. Pentagon only means that there are 5 sides. If you're looking for more definitions, what you're probably going to be looking at is whether something is concave or convex next. And the difference between concave and convex is simply that concave has dents in it, and convex has no dents in it. Now, according to official geometry the thing that makes something concave is that were I to draw a line from each vertex to another, at least one would extend outside of the region. So you can see how this extends outside the region. But it's easier to see physically just by looking at whether or not there are dents. So this would be concave, and this one has no dents, so it's convex. You can look down here and just label them. This is convex, 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 convex. And now here we get to concave because you can see it's dented in. You could draw a line from vertex to vertex that would extend outside. This one would be convex, again, concave, convex, concave. And we would stop there. So when I'm labeling figures, I could say this is a concave dodecagon, or this is a convex octagon. The last thing that we're going to add is these 3 qualifiers, and these won't be in every single figure. For instance, not every figure is equilateral, equiangular, or regular, but they give us a piece of information if they are one of these. So if something is equilateral, it means that the sides are congruent. In other words, their lengths are equal. Now you can see that in the figure below. All of the sides here are equal length. But you'll notice that just because it's equilateral does not mean that all the angles are the same. These two angles certainly look like they're the same, but these two angles, this one and this one, are definitely different from those small ones that we have above. And we might notice some patterns about those later. I've already drawn in the pattern, but just for now, note that equilateral does not mean that they would have equal angles. And that's actually what equiangular means. So sometimes you'll have a figure that is equiangular, and that's where your angles are congruent, or your angles measure is equal. And here you can see a quadrilateral where all of the angles are equal in measure. Now notice again the sides are different, and yes, there's a pattern here, but that's just because of the nature of quadrilaterals, or in this case a rectangle. But it is very clear that our sides are not necessarily equal if we have equal angles. However, if you have something that is equilateral, all the sides are equal, like this, you can see that on this figure, and you have something that is equiangular, we call that a regular figure. Now here in a quadrilateral, if something is equilateral and it's a quadrilateral, and it is also equiangular and it's quadrilateral, it's going to be a square. So that means that these corners are 90 degrees, but it doesn't necessarily mean that in every figure. So let's get to classifying. When we're classifying these polygons, you're going to go with only the information that you have. I'm going to start with convex, concave. I'm then going to name what sort of polygon it is, so sort, and that is the n, the number of sides. And last but not least, I'm going to add whether it might be regular or the equilateral, equiangular. So here, notice how I have signals that each of these angles are the same. Now, even if they don't look the same, the picture tells you they are the same. So that means I will be able to say it's equiangular. I cannot say it's equilateral because nothing tells me that the sides are the same. I can say, so I can actually just add that to my list right now. This is equiangular. And I can say whether it's convex or concave. Well, I see no dents, so that must be convex. And last but not least, I'm going to fill in what sort of figure this is. I like to just do a little dot, 1, 2, 3, 4, 5. That way I know I don't miss a side when I'm counting. So 5 is going to be a pentagon. And yes, I will expect you to memorize the numbers 3 through 12, skipping 11. So this is a convex pentagon that is equiangular. And here with our next one, we can do the same thing. Now notice how we have several different markings here. We've got angles here that are not equal to these angles are all equal. So because they're not all equal to each other, that means that this has to be, or this cannot be equiangular. However, the sides are equal to each other, so that means it's equilateral. So we do have an equilateral one here. I can see that this is clearly concave because I've got dents in it. And I'm just going to do this one as a list since I'm running out of room. And last but not least, let's count these up. We've got 1, 2, 3, 4, 5, 6 sides to this figure, so that is a hexagon. So we've got a concave hexagon that is an equilateral. Now this one I can see right away has all equal sides and all equal angles. That means it has to be regular. And when I count these up, I'm going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that's back to my original. So we have a decagon. And no dents makes this convex. Last but not least, if I'm looking around this, I have no indicators that the sides are equal. In fact, some indication that they aren't. All my angles are different. Notice how it's saying this angle is different than these two, these angles are different than this one, so on and so forth. So that means that it is not regular, it's not equiangular, and it's not equilateral. But I do know that it's convex, or concave, sorry, it has a dent, concave. And when I count it up, I got 1, 2, 3, 4, 5 sides, so that's a pentagon. And I don't need to fill in anything for the last because it's not those things. Now let's see what algebra we can do with this. And what algebra we can do is to do with perimeter, because at this point we're talking about the sides. And in a polygon, any general polygon, you're just going to take the sum of the sides. So if I have here a pentagon, and I have the sides labeled 5, 4, 4, 5, and 3. If I want to find the sum of the sides, or the perimeter, I just do 5 plus 4 plus 4 plus 5 plus 3. And that would give me my total. Of course, you can add in whatever way you wanted, so this would be 10 plus 8, which is 18, and 18 plus 3 is 21. So your perimeter is 21 units, and please remember that you are going to need to include units. If there's nothing listed, just write unit. And that's just how we do it for a regular for a normal polygon. For a regular polygon, we can actually take a bit of a shortcut. So let's say I've been given another pentagon. And let's say that despite how this picture looks, we know that it is equilateral. And maybe even we know that it is equiangular. So this has to be a regular one. If one of these sides is given, it means that I would know what all of these sides are. So I tell you this is 5, that means all the other ones would be 5. Well, that means I'm just adding 5 as many times as I have sides. So that gives us a shortcut, where in a regular polygon, perimeter is going to be equal to the number of sides, and they get this n from what we had above with n-gon, and they're going to multiply that by s, which is the length of sides, length of a side. So here, if I know one is 5 feet, and I know it's regular, I've got 1, 2, 3, 4, 5, so what I'm going to end up with is P is equal to n times s, where n is the number of sides. I've got 5 sides in a pentagon, and s is the side length, which in this case also happens to be 5, but it could have been 4, 2, or 1, and that's going to give me an answer of 25 feet. Now keep in mind, like any formula, that does mean that we can use it in two ways. Let's say I told you that we have a regular nonagon. And in this regular nonagon, we found out that the perimeter is equal to, let's say 45 inches. And I want to know what is the length of the sides. Well, you know the perimeter is 45 inches, and you know that it's regular, so all the sides are going to equal each other, and you know that the number of sides in a nonagon is 9, or at least the chart tells you it's 9. That means that you can set up a formula, because we know P is equal to S times N. And P here is 45, S is unknown, and N is 9. In that case, you can divide both sides by 9, and continuing on with my theme, this does mean that our side length is going to be 5 inches. Last but not least, what I want to talk about for just a moment is circles. And we are going to get to the formula for circumference in a moment, but first I want to just give you 3 terms with circles. Circles are the set of all points equal distance from the center. In other words, it's all the points that are exactly this far away from the center, and I can rotate this all the way around. That's how that center is formed. It's what we're going to do with compasses. But what I've labeled here is r, and r is the radius. It's the distance from the center to a point on the circle. We also have a second one that we talk about quite a bit, and that is our diameter. A diameter is the distance across the greatest part of the circle, or you can think of it as a line extending through 2 points on the circle and the center of the circle. And you can also think of this as a formula where d is equal to 2 times the radius, because it's going to be 2 radiuses added together. There's one other term in here that we have, and that is a chord. A chord is just any connection between 2 points on the circle. So this would be a chord. You'd also have a chord that could extend from here to here.